To illustrate the MCMC algorithm that we just discussed, let's consider an example that it's a mixture of two normals. So the density of the mixture model that we're going to try to fit is going to take the form omega times the square root of 2 pi sigma exp of minus 1 over 2 sigma squared x minus mu1 squared plus 1 minus omega 1 over the square root of 2 pi sigma exp of minus 1 over 2 sigma squared x minus mu2 squared. And this is a mixture of two normals. The weights are omega and 1 minus omega for each one of the two components. The means are mu1 and mu2 for each one of the components. And the standard deviation is sigma for both of them. So this is a location mixture of two normals with a common scale parameter. Before we can derive a Gibbs sampler for this algorithm, we need to first set up priors because we're using a Bayesian approach for inference. So we start with the prior for omega. And in this case, we're going to use a beta distribution with parameters A1 and A2, say. And be careful, this is exactly the same Dirichlet distribution that we just used for the general derivation in the special K where K is equal to 2. In particular, if omega is a beta A1, A2, then omega 1 minus omega, so the joint distribution of the two follows a Dirichlet with parameters A1, A2. So we're just specializing the Dirichlet distribution to the specific case where we have two components. In addition to a prior for the weights for omega, we need a prior for the means, and we need a prior for the standard deviation or for the variance of the model. We're going to use the same prior for both means. We're going to call that prior a normal distribution with parameters eta and tau square. And that implies that the density for my prior, it's going to be of the form 1 over the square root 2 pi tau exp of minus 1 over 2 tau square mu sub k minus eta square. As we will see in a minute, this choice of a normal prior for the mean of each one of the components is computationally convenient and will lead to very simple updates for the value of the parameters. Finally, we need a prior for sigma square. And again, for convenience, we're going to use an inverse gamma prior that you may already be familiar with parameters, say, d and q, which implies that the density of the prior is proportional to 1 over sigma square to the d plus 1 exp of minus q divided by sigma square. And again, just like in the case of the means, for the variances, it's going to be extremely computational convenient to use this type of conditionally conjugate prior. Let's proceed first to write the full joint posterior distribution of all the parameters in the model. And we're going to do that starting with the likelihood for the complete data. That means the likelihood that includes both the observations and the missing data that corresponds to C, the component indicators that we had introduced in previous lectures. So that means that we want the posterior distribution of omega, mu1, mu2, sigma square, and the vector of component C given the data. And if you recall, we defined this as being proportional to the joint distribution of the data given the components parameters mu1, mu2, sigma square, and the indicators C, multiplied by the joint distribution of the indicators, given, in this case, the weight, omega, multiplied by the priors on all the parameters, so the prior on omega, the prior on mu1, the prior on mu2, and the prior on sigma square. Now, given the choice that we had for the structure of the likelihood and the priors in this model, this is going to be proportional to the first term is the product over the components. That in this case, it's only two of them, multiplied by the prior over, or the product over the observations, such that C sub I is equal to K. So just the observations in the case group of their likelihood, that is 1 over the square root 2 pi sigma exp of minus 1 over 2 sigma square xi minus mu sub k squared. So this corresponds to the first term in this expression. The second term in this expression corresponds to our beta prior in this case, because we only have two components. So this corresponds to omega raised to the sum from I equals 1 to n of the indicator that C sub I is equal to k, in this case equal to 1, because it's the first component in the mixture, multiplied by 1 minus omega, sum from 1 to n of indicators that Ci is equal to 2. So this expression corresponds to the second term. And then we can just write the priors that we discussed before. So the prior for omega is omega raised to the a1 minus 1 times 1 minus omega raised to the a2 minus 1. The prior for the mu sub case is the product from k equals 1 to k of 1 over the square root 2 pi tau exp of minus 1/2 tau square mu sub k minus eta square. And finally, the prior for omega that is proportional to 1 over sigma square to the d plus 1 exp of minus d over, q over sigma square. So this is the form of my full posterior distribution. And from this, I'm going to want to obtain a full conditional posterior for omega, given the rest of the parameters. I'm going to want to get a full posterior for mu sub k, given all the parameters. A full posterior for sigma square, given all the parameters, and finally a full posterior distribution for each one of the C sub i's, given the rest of the parameters. And we are going to do that by selecting out from this full posterior distribution the specific terms that contain the variable of interest in each case, and trying to recognize those terms as forming a kernel of a family that we know and can recognize. Let's start with the full posterior for omega, which is very simple. The full posterior for omega, given the rest of the parameters, is going to be proportional to just the terms that contain omega in this big expression. And as you can see, the likelihood for the data does not contain omega anywhere. And the priors for mu1, mu2, and sigma, that are these expressions down here, do not contain omega in any way. So the only terms that are left are this piece here that corresponds to P of omega, the prior, and this piece here that corresponds to the distribution of the indicators given the weight. So this just becomes proportional to omega to the sum from 1 to n of indicators that c sub I is equal to 1 multiplied by 1 minus omega, sum of indicators that c sub I is equal to 2, multiplied by omega, a1 minus 1, 1 minus omega, a2 minus 1. And we can obviously pull terms together, so we can pull the two omegas together and the two 1 minus omegas together to just write this in the form of omega raised to, let's call it a1 star minus 1, 1 minus omega, a2 star minus 1, where a sub 1 star is just a1 plus this exponent here. And a sub 2 star is my original a sub 2 plus the number of observations that are currently assigned to the second component. So we can recognize this kernel here as exactly the same kernel of the beta distribution that we used as a prior. So that just means that the full conditional of omega, given the rest of the parameters, is a beta with these updated parameters, a1 star and a2 star. By the way, in the future, it will be convenient to simply call n sub 1 the sum from 1 to n of the indicators of c sub I is equal to 1, and n sub 2 the sum from I equals 1 to n of the indicators that c sub I is equal to 2. So as we did with the general formulation of the model. In that way, these expressions can be written in a slightly shorter way, and I will be using this type of notation later on for other full conditionals. Let's proceed now to derive the full conditional distribution for the indicator c sub I that tells us what component generated the ith observation. In other words, we want the density or the probability that c sub I, and because c sub I can only take two values, you can only come from component 1 or component 2, it is enough that we look at the probability that c sub I is equal to 1. And we can always obtain the probability that c sub I is equal to 2 by doing the complement. So this expression is proportional to only the terms in here that contain c sub I, and in particular that contain c sub I equal to 1. And if we look at this carefully, there are only two terms, one that comes from this product. And again, this is a product over many observations, but only one term in that big product is going to participate in this full conditional. And similarly here, there is only one term that has to do with c sub I equal to 1 that is a term that has to do with omega. So this becomes omega, that is a term that comes from here, multiplied by the single term that comes from here, that is 1 over square root 2 pi sigma exp minus 1 over 2 sigma square xi minus mu1 square, which means that once we renormalize, the probability of c sub I equals to 1 given all the parameters, it's going to be proportional to, or excuse me, equal to omega exp of minus 1 over 2 sigma square xi minus mu1 square divided by omega exp minus 1 over 2 sigma square xi minus mu1 square plus 1 minus omega exp of minus 1 over 2 sigma square xi minus mu2 square. Where, as you can see, I did a couple of simplifications. In particular, 1 over square root of 2 pi sigma is going to appear in front of each one of these terms, so I can cancel them out. That's a simplification that happens because I have the same sigma for all components in my mixture. Let's look now at the full conditional for sigma square for the variance of our kernels. We want the full posterior distribution of sigma square given the rest of the parameters. And again, all the terms that are involved in this double product here involve sigma, so I need to retain all of those for the purpose of computing the full posterior. And the other term that contains sigma is the terms that come from the prior down here. So I can ignore all these pieces that have to do with the prior on omega, the prior on mu, and the distribution of the indicators given the weight. So that means that this term is going to be proportional to. And I'm going to start to do a couple of simplifications here. So one of them is I'm going to write sigma as sigma squared raised to the 1/2. So I'm going to have 1 over sigma squared raised to the 1/2. And then I have a product over the observations and a product over the a product over the components times a product over the observations that belong to that component. If you look at this carefully, we basically have as many terms as observations, and all of them involve this 1 over sigma squared to the 1/2. So in reality, I can just raise this to the n, that is the number of observations, multiplied by the exponential of. And now I do need to take my terms inside. So this is minus 1 over 2 sigma squared. These products become sums. So I have a double sum from 1 to capital K. And then for the i's such that c sub I is equal to k of xi minus mu sub k squared. And of course, the terms from the prior, 1 over sigma squared to the d plus 1, exp minus q over sigma squared. And again, as I did before, I can try to pull together terms that have the similar structure. So this is going to be equal to 1 over sigma squared to the, let me call it d star plus 1 times exp of minus 1 over sigma squared q star, where d star is just my original d plus n halves, and q star is my original q plus the term that is in here, that is 1/2 of the double sum over the k's first and over the i's that belong to the k's component of xi minus mu sub k squared. So in other words, we get a posterior distribution that has exactly the same form as the prior that we started with, but with updated parameters d star and q star, which allows me to just say that sigma squared, given all the other parameters, just follows an inverse gamma distribution with parameters d star and q star.